Welcome back, everyone, for another deep dive. This time, we're tackling a topic that you guys have been asking about for a while now, hydraulic fracturing. We're going to get down to the basics, how it works, the why, what makes it successful. We've got chapter 2 from a book all about hydraulic fracturing. And let me tell you, I'm already learning so much more about the nuts and bolts of this whole technique.
Yeah, it's one of those things that gets, talked about so much, but I think the actual science behind it kind of gets lost in all the noise. So
Hmm,
hopefully by the end of this deep dive, you'll have a much clearer picture of what's going on down there, thousands of feet underground.
definitely. So let's start with the most basic question here. What exactly is hydraulic fracturing?
Well, at its core, it's a pretty straightforward concept, believe it or not. It involves pumping fluid down a well bore at really high pressure, high enough to actually fracture the surrounding rock. And that creates a pathway for oil and gas to flow more easily into the well.
So we're talking about intentionally cracking the rock open. Sounds pretty intense.
It is intense, but it's not random. The fracture that's created actually takes on a very specific shape, kind of like a flat, hot water bottle. And this is where the real ingenuity comes in. That shape is designed to maximize the surface area for oil and gas to flow through while using the least amount of fluid possible. It's all about efficiency.
That makes sense.
Yeah.
I guess, though, why not just drill a well and let the oil and gas flow naturally? Why go to all this trouble to fracture the rock in the first place?
You've hit on a really key question there. There are actually three main reasons why hydraulic fracturing has become so widely used these days.
Okay, I'm all ears.
Well, firstly, it can be used to bypass damage around the well bore itself. Over time, the area around a well can get clogged up with debris, drilling mud, things like that, and that hinders the natural flow of oil and gas. So fracturing kind of creates a clean path through that damaged zone, almost like hitting a reset button on the well's performance.
Interesting. So you're saying it's about restoring the well's natural productivity.
Exactly. But it's not just about restoring things back to normal. We can actually boost production beyond natural levels. And that brings us to the second reason, increasing productivity. By extending that conductive channel deep into the reservoir, we can tap into reserves that would otherwise be, well, really difficult to reach.
I'm seeing a theme of efficiency here. And this is where Darcy's law comes in, right?
You got it. Darcy's law essentially tells us that the flow rate depends on several factors, but one of them is the flow area. So by increasing that area through fracturing, we can directly increase the production rates. It's kind of like adding extra lanes to a highway, for oil and gas to flow.
That's a great analogy. Okay,
Mhm.
so what's the third reason?
Well, the third reason is about the bigger picture, reservoir management. You see, fracturing isn't just about individual wells anymore. It's about strategically altering the fluid flow within the entire reservoir.
Wait, hold on. Are you saying we can actually control how the oil and gas moves underground?
To a certain extent, yes. And this is where it gets really interesting. By selectively fracturing certain zones, we can optimize recovery, meaning we can extract a greater percentage of the oil and gas that's actually present. It can even influence where we decide to drill future wells, maximizing the overall efficiency of the entire field. A really great example of this is the Gulfax field in the North Sea. They actually used selective fracturing to manage sand production, which is a big challenge in those reservoirs. By carefully controlling where the fractures formed, they could maximize reserves and prevent, having to abandon wells prematurely.
That's remarkable. It's not just about brute force, huh? It's a really calculated technique.
Precisely. But designing those fractures and making sure they're actually effective involves a lot of different variables, and understanding them is key.
Okay, well, let's get into the details. What kind of variables are we talking about? And how do they actually impact the success of a treatment?
Well, one of the most important aspects is the fracture geometry itself. The height, the length, the width of the fracture. Each of those dimensions plays a role in how well the fracture can enhance production.
So it's not just about making a crack, it's about making the right crack.
Absolutely. To get it right, engineers actually have to consider two sets of variables. First, there are the in situ variables, which are the inherent properties of the rock formation itself. These are the things we can't really change. It's what, nature has given us.
So what kind of properties are we talking about?
The critical ones can be remembered with the acronym HECK. So we have height of the fracture, Young's modulus, that represents the rock stiffness, the fluid loss coefficient, which tells us how much fluid leaks into the surrounding rock, and finally, fracture toughness, a measure of how resistant that rock is to cracking.
HECKI. I'll have to remember that. But these are all set in stone, right?
Right. But knowing those parameters is essential for making informed decisions about the treatment itself. And that brings us to the second set of variables, the treatment-specific ones. These are the things we can control, like, how fast we inject that fluid, the viscosity of the fluid, and the total volume we pump.
So it's almost like a game of chess. You've got the board set up by nature, and then you have to make strategic moves with these treatment variables.
That's a really good way to put it. One of the most fundamental concepts that links these variables together is material balance. Essentially, the volume of that fracture is determined by the amount of fluid that's pumped in minus the amount that leaks off into the surrounding rock. Think of it like filling a leaky bucket.
Right, the final amount of water in the bucket depends on, how fast you're pouring and how much is leaking out.
Exactly. Now, let's break down some of these variables and, how they impact the fracture geometry, starting with fracture height. This is arguably the most important factor, and it's primarily controlled by the stress differences between the pay zone, that's where the oil and gas are, and the surrounding rock layers.
So if the pressure is higher above and below the pay zone, it's like the surrounding rock is squeezing the fracture, limiting how tall it can grow.
Exactly. And controlling the height is a tricky business. If it grows too tall, it could actually hit an undesirable zone, like a water formation, or it could actually limit the fracture's length, reducing the overall effectiveness.
It's a real balancing act. Now, what about that fluid loss we were talking about earlier?
Right, so there are two key components controlling that, the fluid loss coefficient and the spurt loss.
Remind me, what was that fluid loss coefficient again?
It's a measure of how easily that fracturing fluid escapes into the surrounding formation. Several things play into this, like the filter cake. That's a layer of solids that builds up on the fracture face. Then there's the mobility of the fluid itself and the compressibility of the reservoir fluids.
So a lower coefficient means less fluids being lost, which is generally good, right?
Exactly. And then you have the spurt loss, which is, that happens right when that fracture initially forms. It's like that initial burst of fluid loss. It usually plays a smaller role compared to that continuous fluid loss that's governed by the fluid loss coefficient.
Okay, so it's like the difference between a sudden spill and a slow leak.
Perfect analogy. Now, predicting fracture width directly has historically been a challenge. So engineers kind of shifted their focus to something called net pressure. That's essentially the pressure difference that's driving both the creation of the width and also how that fracture propagates.
And net pressure is something we can actually predict and measure, right?
Yeah, that's right. And it directly relates to the width through something called the Sneddon equation. Simply put, wider fractures require higher net pressure. It's kind of like blowing up a balloon. The more air you put in, the wider it gets.
More pressure, wider fracture. Got it.
Mhm.
You mentioned there were two components of net pressure, though.
You're right. There's the pressure that's needed to actually force that fracture tip to grow. We call that P-tip. And then there's the pressure that's lost due to friction as the fluid travels along the fracture. That's P-viscous.
So it's like a constant battle between the pressure pushing the fracture forward and the friction trying to hold it back.
Exactly. And the balance between those two components can really vary. Sometimes P-tip dominates, and you get these wide fractures where friction's not really a big factor. Other times, P-viscous takes over, and the pressure at the tip becomes less important. It's their combined effect that determines the overall net pressure and therefore the fracture width.
Okay, so we've covered pressure, fluid loss, height. What about figuring out the overall dimensions of the fracture?
Well, that's where we turn to fracture geometry models. And this is where things can get a little heated in the world of hydraulic fracturing.
Sounds like there's a debate brewing. Tell me more.
Well, there are two main 2D models that have been used for years. The Perkins-Kern model and the Gritsma-de Klerk model, or PKN and GDK for short. Each of those models is based on different assumptions about the relationship between the fracture's length and height.
So which one's the right one?
That's the million-dollar question, isn't it? The PKN model assumes long fractures, much longer than they are tall. This model works well in situations where the pay zone, the layer we're targeting, is thin. The GDK model, on the other hand, assumes tall, short fractures, more suitable for those thicker pay zones.
So the choice of model depends on the specific characteristics of that reservoir.
Precisely. Think of it like a sheet of paper for PKN and in a tall, narrow book for GDK. There's even a radial geometry model for cases where the height and length are about equal.
Sounds like a model for every occasion.
You could say that. But here's the fascinating part. Neither 2D model perfectly reflects reality. The ideal model actually depends on how that fracture grows over time, which can be, quite dynamic.
There's certainly a lot of complexity here. How do engineers manage all of this in the real world?
Well, that's a great question, and that's what we'll dive into as we continue our exploration. Trust me, there are methods and technologies that help engineers navigate all of this and design effective fracturing treatments.
Yeah, it really is mind-boggling to think about all these things happening down there. So how do engineers actually make sense of all of this, all these variables when they're designing these treatments?
Well, it really is a testament to human ingenuity, isn't it? Figuring out how to manage all this. One of the most valuable tools in their arsenal is fracture modeling software.
Okay, tell me more about that. What does it actually do?
Well, these programs are incredibly sophisticated. They allow engineers to basically simulate different fracturing scenarios. Factoring in all those variables we've been talking about, they can essentially run these virtual experiments, tweaking things like the pump rate or the fluid viscosity or the amount of proppant to see how those changes impact the fracture geometry and ultimately how they affect the production levels.
So it's like a virtual sandbox where they can kind of test out different approaches and optimize that treatment, before they even actually set foot on a well pad.
Exactly. It's a powerful way to reduce uncertainty and increase the likelihood of success. But it's not just about the software, of course. Experience plays a huge role as well. Those seasoned engineers, they kind of develop this sixth sense for how different rock formations will react to fracturing. They bring a wealth of knowledge about geology, rock mechanics, fluid behavior, all that to the table.
So it's a blend of cutting-edge technology and good old-fashioned human expertise.
Precisely. And both of those areas are constantly advancing. For example, there's a technique called microseismic monitoring that's becoming increasingly popular these days that involves using sensitive equipment to essentially listen for the tiny seismic waves that are generated as the fracture grows. This gives engineers real-time feedback on the shape and the extent of that fracture.
Wow. So they can actually listen to the rock cracking underground. That's amazing.
It is, and it allows them to, make adjustments on the fly if needed, making sure that fracture stays within the desired zone and avoids any unwanted surprises.
That level of precision is incredible. It's like they have X-ray vision for what's happening below the surface. But I'm sure there are still challenges, right?
Yeah.
Even with all these advancements.
Oh, of course. It's a constantly evolving field. One of the biggest ongoing challenges is predicting how the proppant is going to be transported within that fracture.
Okay, back up for a sec. Remind me what proppant is and why it's so important.
Sure. Proppant refers to those tiny grains of sand or ceramic material that are pumped into the fracture, along with that fracturing fluid. They're really the unsung heroes of this whole operation. You see, their job is to lodge themselves within the fracture as the pressure drops, preventing it from closing up completely. It's kind of like putting, tiny wedges in a doorway to keep it open.
Right, those proppants are what keep those pathways open for the oil and gas to flow. But you're saying getting them to the right place is tricky.
It is. Getting the proppants to settle evenly throughout the fracture and create that optimal flow path is, well, it's a complex challenge. It's a delicate dance, involving factors like the viscosity of that fluid, the size and the density of the proppant, and of course the geometry of the fracture itself.
So what are some of the potential problems then if that proppant doesn't distribute evenly?
Well, if too much proppant settles near the wellbore, it can create kind of a bottleneck, restricting that flow. And if there's not enough proppant further out in the fracture, that part could actually close up prematurely, limiting production.
So it's about finding that Goldilocks zone, just the right amount of proppant in just the right places.
Exactly. And there's a lot of ongoing research and development focused on improving proppant transport and placement. For example, they're developing proppants with special coatings that can improve their flow characteristics, and help prevent settling. There are also techniques that use foam or other diverting agents to direct that proppant flow more effectively.
It's fascinating how much science and engineering goes into something that at first glance seems so simple, right? Cracking open a rock.
Yeah, it really highlights the ingenuity and that drive to constantly improve efficiency, in this industry.
So we've covered the basics of what hydraulic fracturing is, why it's done, and some of those key factors that influence its success. Is there anything else that you really want our listener to kind of walk away with here?
I think the key takeaway is that hydraulic fracturing is a powerful technology with, the potential to unlock vast reserves of oil and gas, but it's a complex process. It requires careful planning, execution, monitoring to ensure it's done safely and responsibly.
Yeah. It's about striking that balance between maximizing production and minimizing the potential risks, right?
Exactly. And that requires ongoing research, innovation, and a commitment to best practices from everyone involved.
We've talked a lot about the what and the why of hydraulic fracturing, but there's a whole other piece of this puzzle that we haven't really touched on, the how.
You're right. The actual process of carrying out a hydraulic fracturing treatment, that's fascinating in itself. There's all kinds of specialized equipment, a carefully choreographed sequence of steps, a whole team of skilled professionals working together to make it happen.
Okay, so paint us a picture. What actually goes on, out there on that well pad when they're conducting a fracturing treatment?
Okay, well, imagine this. You're standing on a well pad, which is basically this flat, cleared area where all the equipment is set up. The first step is to isolate that zone that they want to fracture. They do this by placing something called packers. They're kind of like expandable plugs above and below that target interval.
So it's like creating a sealed chamber within that well bore, so you're focusing the pressure on that specific section where you want that fracture to form.
Exactly. Once that's done, they start pumping that fracturing fluid down the wellbore, and they gradually increase the pressure as they go.
What exactly is fracturing fluid, by the way? What's in it?
Well, it's a mixture of water, sand, and various chemicals. Each ingredient has a specific purpose. Some of those chemicals act as friction reducers, making it easier to pump the fluid at those really high rates. Others help control the fluid loss, minimizing how much leaks out into the surrounding rock. And then you have chemicals that help break down gels or other additives after the fracturing process is complete. This helps ensure that the fracture, now packed with that proppant, remains highly conductive.
So it's a carefully engineered cocktail designed to achieve very specific goals.
Precisely. As the pressure continues to build, it eventually surpasses the strength of the rock, and that's when the initial fracture forms. That's often referred to as the breakdown phase.
It's got to be a pretty dramatic moment.
It can be. You might actually hear a loud crack as the rock gives way,
Yeah.
and the pressure gauges, they suddenly drop as that fracture forms. From that point on, the fracture continues to grow, as more and more fluid is pumped in, extending outward from that well bore.
And this is where those prop hands come in, right? To hold that fracture open after they start pumping.
Exactly. They're mixed into that fracturing fluid and carried along as that fracture grows. As the pumping rate slows down and the fracture starts to close, those prop ends lodge themselves within the fracture, preventing it from completely shutting.
So they're like tiny supports holding that pathway open. How do they control where those prop ends end up, though? How do they ensure they're, evenly distributed throughout the fracture?
Well, that's one of the big challenges in hydraulic fracturing. Like we mentioned earlier, it's a complex interplay of factors. Engineers use different techniques to try to, optimize proppant placement. One approach is to adjust that pumping schedule, starting with a lower concentration of proppant and gradually increasing it as that fracture grows.
So it's about carefully timing the release of those proppants, making sure they reach the furthest parts of that fracture.
That's right. And they also use techniques like diverting agents or foam to help, direct that proppant flow more effectively to try and achieve a more even distribution.
It's amazing how much thought goes into, optimizing every single step of this whole process.
It is. Once they're confident the proppants are in place, they'll stop that pumping process, and the well is allowed to flow back.
Okay, so what exactly happens during flowback?
Well, during flowback, some of that fracturing fluid, along with any hydrocarbons that have entered that fracture, flow back up to the surface. That fluid is carefully collected, and they either dispose of it properly or they treat it and reuse it.
So it's a controlled release of pressure and fluids.
Exactly. And once that well is stabilized, it can be put into production. And oil and gas are now flowing more easily through that propped open fracture.
So we've gone from fracturing the rock to propping it open to flowing back the well, and finally to achieving that increased production. It's a multi-stage process that requires incredible precision and coordination.
You got it. And that's just a simplified overview. There are many other aspects to hydraulic fracturing, including monitoring the well's integrity, managing the environmental impacts, and of course ensuring the safety of the personnel and the surrounding community.
It's clear that hydraulic fracturing is a multifaceted technology. It requires expertise from all kinds of different disciplines.
Absolutely. And we're constantly learning and refining these techniques to try and and make this process more efficient, effective, and environmentally sound.
So it definitely sounds like there's this whole other layer of things to consider beyond just the technical parts of the process. What are some of the main environmental concerns around hydraulic fracturing? And how is the industry working to address them?
Well, that's an important question. Some of the biggest concerns revolve around water usage, the potential for, groundwater contamination, and induced seismicity.
Okay, let's break those down one by one. First, water usage. We've talked about how this technique uses large volumes of water. So how is that being managed, especially in those areas where, water resources are already pretty stretched thin?
Well, it's true that hydraulic fracturing can be water intensive, but the industry has made some pretty significant strides in reducing the amount of water used, and they're exploring those alternative sources. For example, a lot of operators are now using recycled water, what we call produced water, water that's already been used in other oil and gas operations. So they're not drawing from those fresh water sources as much.
So it's about minimizing the impact on those freshwater supplies and finding ways to reuse what's already available.
Exactly. And there's even research being done on, completely waterless fracturing techniques using things like liquefied petroleum gas or, other fluids instead of water. Those technologies are still in development, but they hold a lot of promise for reducing the overall water footprint of hydraulic fracturing.
That's encouraging to hear. What about the risk of groundwater contamination? It seems like that's a big concern for a lot of people.
Oh, it's an understandable concern. And it's, one that the industry takes really seriously. The primary defense against groundwater contamination is well integrity. Those layers of steel casing and cement that we were talking about earlier, those act as barriers, preventing those fluids from migrating outside the wellbore and into, the surrounding rock
This
formations.
is like a series of protective shields isolating those fracturing fluids from those groundwater aquifers.
That's a good way to think about it. And there are very strict regulations and industry standards in place to ensure that those barriers are installed and maintained properly. Operators regularly conduct pressure tests, inspections, things like that to verify the well's integrity throughout its operational life.
That makes sense. I do have to ask, though, what happens if something does go wrong? What if there is a leak or a spill despite all those precautions?
Well, in those rare cases, it's really crucial to have, a robust monitoring and response plan in place. Operators continuously monitor the groundwater quality in the vicinity of those wells, and they have really detailed procedures for containing and cleaning up any spills or leaks that might occur.
So it's about having multiple layers of protection, preventing the contamination in the first place, but then also being prepared to act quickly if something does happen.
Right. Now, the third concern we mentioned was induced seismicity. That's the, potential for hydraulic fracturing to trigger earthquakes.
Yeah, I've heard about that. How does that actually happen, and how big of a risk are we talking about here?
Well, it's important to note that, the vast majority of hydraulic fracturing operations, they don't trigger any noticeable seismic activity at all. However, there have been some cases where the injection of those fluids deep underground, it alters the stresses along those existing fault lines. And this can cause those faults to slip, resulting in an earthquake.
So it's not the actual fracturing itself that causes the earthquake, but those changes in pressure and stress that result from it.
Precisely. And this is a relatively new area of research. Scientists are still working to understand those mechanisms that are involved. But there are definitely steps that operators are taking to mitigate the risk.
What kind of steps?
Well, one approach is to carefully select those injection sites, avoiding areas with those known active faults. They also they monitor the seismic activity during operations, and they can adjust those injection rates or the pressures if needed. In some cases, they might even choose to halt operations entirely if there's a concern about triggering a significant seismic event.
So it's all about understanding those potential risks, taking a science-based approach to minimize them, and then having those, contingency plans in place.
Exactly. And as our understanding of induced seismicity continues to evolve, we can expect to see even more sophisticated mitigation strategies being developed and implemented.
It seems like with any, really powerful technology, there are bound to be challenges
Yeah.
and potential risks. But it's clear that a lot of effort is going into addressing these concerns and finding ways to make this whole process safer and more sustainable.
Absolutely. And that ongoing effort is crucial as we continue to, rely on oil and natural gas to meet our energy needs. It's imperative that we develop and deploy technologies like hydraulic fracturing in a really responsible and environmentally sound manner.
Well said. Wow, we've covered a lot of ground today, going all the way from that basic definition of hydraulic fracturing to the complexities of, designing effective treatments and all of the those environmental considerations that come into play.
We have. You now have a pretty good grasp of, why these fractures are created, how that shape is influenced by so many different factors, and what engineers really have to consider when they're designing these treatments. Plus, you're aware of those environmental questions surrounding the technology and, all the efforts that are being made to address them.
This is exactly the kind of deep dive I love. A chance to, unpack a complex topic and walk away with a much better understanding of how it works and why it matters.
I agree. But before we wrap up, though, I do have one final thought-provoking question for you to consider.
Bring it on. I always love a good brain teaser.
Okay, well, think back to everything we've discussed today. How do you think the viscosity of that fracturing fluid, its thickness, essentially, might impact that resulting fracture geometry and the overall success of a treatment?
Ooh, that's a good one. It really pulls together so many of the concepts we've talked about today, fluid flow, pressure distribution, proppant transport. I'm going to have to think about that one for a while.
It's a question that really highlights, just how interconnected all those variables really are and how crucial that careful design and execution are in hydraulic fracturing.
Well, on that note, we'll wrap up this deep dive into hydraulic fracturing. It's been a fascinating journey. We'll be back soon with more deep dives into other intriguing topics. Until then, keep those brains buzzing, and thanks for joining us.